Good morning. It's my great pleasure today to introduce our newest member of the Electrical Engineering Department here at the University of Washington, Dr. Brandon Pierquet. Dr. Brandon Pierquet got his bachelor's degree from the other university, which is also known UWEE, which is University of Wisconsin. Then he went on to get his master's and PhD degrees from MIT. He worked at Enphase Technology as a senior design engineer and joined us earlier this year. Brandon?
Thank you very much for the nice introduction. Can everybody hear me okay? Okay. So as Daniel said, my name is Brandon Pierquet. The title that we're going to work with is essentially power conversion for photovoltaic systems. We'll talk a bit about the distributed versions versus the centralized ones. We'll go over what might be slightly redundant to many that work in energy, basically solar as the energy source that we deal with, as well as just some basics about photovoltaic operation, the cells, and their behavior. Then some of the complications in moving up with making cells turn into modules and modules turn into arrays, and where that gives us challenges we have to overcome and also opportunities for making things better. And then we'll go into a bit into the conversion architectures in terms of the system level. How do you distribute the modules amongst different inverters if it's grid connected? And at what level do you put these converters, whether they're going to be located with individual processing, if they're going to be aggregate with a single centralized version, and then we'll just do some quick conclusions. So solar is an energy source. Most people have probably seen something like this before. In this case, it shows a number of circles representing the amount of energy that's available. Those along the left-hand side, center to left, those are going to be the renewable ones. And that's the renewable amount of energy per year available. Whereas along the right-hand side, the fossil fuel-based and essentially other limited resources, that's the total known availability. And so if you can capture a lot of this extra renewable sources, we can easily eclipse what we would normally have for a lifetime given the other sources. And so solar is obviously a very large energy source that we can use. There are problems with where we capture this and how we do it, but it's a very, very large place to get it. It's also the only nuclear fusion energy source that we have available to us on Earth. So where does the solar work the best? This is just solar insolation. Basically how much energy falls onto a module of a given size over the course of a day. And it's pretty clear that in the Southwest, California, Nevada, Arizona, New Mexico, it gets the most insolation. Now, this is not necessarily correlated directly to the amount of energy you can get out of a module placed at a location anywhere on this map. A lot more goes into what energy capture can actually occur. And so this is a little bit misleading. In a lot of the very, very warm climates, the photovoltaics tend to become less efficient. So when it's Southern California in the middle of the summertime and it's 100 degrees on top of a building, those solar modules are substantially less efficient, at least for the silicon ones that are most popular, than they would be if it was northern Minnesota in the winter, 40 below zero. And so the actual energy generation capability per location in the U.S. has a much more complicated structure depending upon the time of the year. But in general, this is essentially where the most sunlight occurs in first-order approximation, one of the better areas to be targeting. That unfortunately leaves most of the eastern U.S. a little bit lacking. So if we look at what the eastern U.S. looks like, and even the northwest up here, relative to the world, we can see that most of the U.S. here is actually somewhat in the orange, maybe not the dark orange, but if you look at where Europe is, particularly Germany, Netherlands area up here, they actually receive substantially less total insolation than we do. Yet they are one of the world's leaders in penetration of PV in their power system. And so they've been highly successful in turning a lot of their energy usage coming from PV and wind and other sources, even though they effectively will have less sun available to them than we do here. And so that essentially tells us that we have really good opportunities throughout the entire U.S. to be taking advantage of this. So I'm just going to give you a few photos of what these typical installations look like. You've probably seen some of these. This is simply a rooftop installation. Each one of those modules is probably 200 watts. So with 10 of them, you're looking at just single-digit kilowatts. It's not a lot of energy, but it's also a very small home. And so ultimately, that may completely take care of, on average, their usage of energy in the home. Certainly, they won't be using every amount, every watt that comes out at the time it comes out, but that extra energy is pushed back onto the grid, and then it's taken back off when it's used. And so their net energy transfer is going to be less. This is a very large warehouse outside of Denver, Colorado. This is about a 250 kilowatt system. I had a chance to visit and actually see this. This is a situation where in the summertime, this is really hot. On top of the building, it's probably 110 degrees. It's about 100 in the shade. And so these solar modules are at a very, very high temperature. So in the summer, they're actually not producing a whole lot of energy. And in the wintertime, even with lower amounts of sunlight, they actually don't produce much less power than they do in the summertime. And so that's a relatively large flat roof installation and somewhat of a traditional method of installing these. There are a couple other non-traditional installations. These are massive solar trackers. In these cases, they actually happen to be concentrated photovoltaics. And so they actually take these trackers and they move them along with the sun. I believe these would be a 2-axis tracker, so they can actually change with the seasons as well as the day-to-day variations. Most of these types of systems are actually based on the same mechanics that operate radio telescopes. And so there's a bit of economy of scale, even though the scale is very small, in order to have these. And so I think each one of these particular trackers puts out multiple hundreds of kilowatts. And so there are 16 of them at this site, and they're very, very large. This happens to be a technician standing underneath it. So the scale of these can be quite large, and this isn't necessarily the largest tracker that's around. So we'll talk a little bit about photovoltaic basics, how the cells work, what we care about in terms of their behaviors, and hopefully there's a little electrical engineering behind this, so hopefully everybody knows a little bit of circuits. So a cell is basically a diode. It just so happens that when sun is shined onto it, it generates excess currents or electrons in the material, and then those are extracted through the essentially positive negative side of this. So it's sort of, it's basically a diode. It just happens to use the sun as an input source to generate the electrons, the energy for them. But the issue being, just like a diode, it's relatively low voltage. And so one of the trade-offs is the size that you make these. You can't really increase the voltage by the cell itself. Different materials will give you different voltages. Silicon, whether it's monocrystalline, polycrystalline, even amorphous silicon, are going to have a different voltage range depending upon how they're manufactured and just process variation. But it's typically low, below a volt, or below 2 volts even for thin film. And so in order to do something more useful with this, they essentially scale up the area so they can get a reasonable amount of current. So if you were to make a power converter that handled 1 volt at 10 amps, it's not terribly efficient if you're trying to put it on the grid. It's a pretty large transformation ratio that you need to achieve. And so we'll talk about that in a second, but if you want to model this in a circuit, what you end up looking at is a somewhat complicated model, at least a first-order model, that sort of captures the photovoltaic current, essentially the current due to the incident light. You have a diode. It's essentially a PN junction style, and so you have the diode behavior. And then you have parasitics. You have some series resistance connection that comes in from just the wires that connect this together. The conductors on top of the cells themselves, a lot of them are translucent or they're somewhat patterned, so they're not terribly conductive compared to a solid copper wire. And then you have some shunt resistance, which is essentially a recombination of the energy inside, which never actually makes it out. And so if you go ahead and you actually write out this first order model, you end up with something that isn't explicitly solvable because the current depends upon the current itself. And so this is something you actually have to just do numerically in order to get the result. And so oftentimes we use the simplified version of it where we have no series resistance, and in this case also no shunt resistance. And that gives us a substantially easier equation to be dealing with. And when you're doing this zero-order model approximation, for much of what you're doing, if you're looking at the larger scale aspects, it's usually pretty good. It's not quite everything you want if you want really fine details in your behavior. However, it's for a purpose of demonstrating and understanding. It's a pretty effective tool. So how does this change during the behavior of the cell during different illumination periods? So in this case, we have increasing irradiance coming in. And so this happens to be, you can see that we'd say have a photo current of 2 amps and then 4, 6, and 8. And so it's going to generate these curves. This is essentially current on the y-axis and voltage along the x. And so there are 2 points of interest initially. One of them is going to be the open circuit voltage. Basically, when there's no current coming out, there's a particular voltage that it will achieve just due to that current being pushed into the diode and not out of the cell itself. And then the sorry about that. And then the short circuit current, which is what happens if you just throw a wire across the output. That's essentially going to be taking all of the photocurrent out and shorting it out. And so those 2 places have no power delivery. You may have 100 amps, but at 0 volts, that's 0 watts. And same with that open circuit voltage. You have no current, and so you're at 0 power there. So you can imagine somewhere in between you're going to get real power out of this. And there's a point on the curve at which you actually achieve the maximum voltage current relationship. Now, this is essentially doing the maximum power theorem and figuring out what the impedance of the cell is at a given place, and that effective resistance changes because it's nonlinear. And so as you have these curves, I took a chance and I dotted where the actual peak power location occurs on these. And you can see that it's not at a constant voltage along the curve, and it's certainly not at a constant current because that's what we're varying with the different sunlight. And so this voltage will actually change over time depending upon what the incident light is. So the larger radiance essentially results in larger power. So if you look at these dots, for the blue, green, the red, and cyan, they're going to be essentially correlated vertically with each of the plots up and down. And so this kind of gives you an idea of what the power output looks like relative to the voltage that's across this. And in this case, when you decide to interface to this, you have to be the one as a power converter or as a circuit trying to figure out at what voltage do I need to run in order to have the current be at the point that it's needed to get the maximum power out. And so there's actually an active feedback role in the conversion process in order to get the converter operating at that point. So we'll talk a bit about building up modules and arrays. We didn't talk before about the non-ideal ideal factors a little bit, but we'll cover this here to an extent. So as you create a module, one of those cells, they're usually made at this point from 6-inch wafers, simply because 30 millimeter wafers from the semiconductor manufacturing industry are pretty much the norm at this point. And so the larger the area you can use in a single cell, the more efficient it is to actually produce. And so they've essentially adopted whatever the technology is that the rest of the semiconductor industry uses. And so that particular area is going to determine what current it can put out. And so in this case, they're sort of stuck. They're at 6, 8, 10 amps, depending upon the material, just given the size they're at. And so in order to get more power out of a module, you increase a whole bunch of them in series. So you basically connect them in series. On the top, there's metallization that connects across and over, and it connects to the one right below it. And so it's essentially series stacked, one on top of the other, in order to get the bottom terminal underneath connected to the top terminal of the next one. So simple ribbon connections soldered to the tops of the cells, and they just pile these up to make nice little strings. So in this case, we get the same amount of current through each. It's just a series connection. There's no other place for current to go but through each one. And so in this case, essentially all you're doing is summing up the additional voltages. So the currents are constant. And so if you generate the new IV curve, you will have the exact same current profiles. All that's going to happen is your voltage range is going to stretch out. And so in this case, if you had, say, a 1 volt cell and you've got 7 of these. Now you're up to 7 volts. And that tends to be the way they do this. In most cells now, in most modules now, the typical quantity is 60 cells, which gives you about 40 volts maximum output, and ultimately you're running in the range of 24 to 30 volts. And so they stack these up with quite a large number. This only works well when each one of these cells is matched. So we should sort of assume that they're all perfect. And depending upon what cell technology you're using, they very well may be close or really close. When you're doing the monocrystalline silicon cells, they come out of batch processing. They then flash test them, and they bin them based on their performance. So when they build a module, they'll build a module of 60 cells, which are pretty closely matched. And so that's not necessarily a big problem with those. Other materials do have a substantially larger variation. And so you have to kind of consider what happens when you don't have good matching. So in this case, even though we have a small shaded cell, a small portion of a shaded cell, we still have the same current through each cell. It just so happens to be that now one of these cells has much less capability of generating current than the others. And so now all of the other ones suffer. And so what you end up with essentially is the same situation you had before, where you're summing up all of the voltages based on the currents that they can use. And the current that you can get out of it is nothing more than the maximum of the minimum one producing power. And so in a string like this, if you have a small shading or a slight mismatch between cells, it may not be the end of the world. You may be losing a fraction of the power. But if you lose one cell due to any sort of soiling, bird droppings being unfortunately very common occurrence, and that effectively will cut out the power of a whole entire module, depending upon where it lands and how much it covers. Leaves are another major cause of these. And so matching that is very important. There are other issues involved other than just the loss of power. If each one of these cells is putting out a substantially large voltage because it can't use all of its current, so its voltage goes up a little bit, and there happens to be a known voltage applied across there because you have some sort of power conversion circuit that's holding a voltage, this cell here can actually become reverse biased. So the total will ultimately mean that this may become with a negative voltage. That means it's going to start to push more current into the cell instead of out. What that will cause essentially is localized heating. Because these aren't perfect materials and there are defects, what it's going to do is force the current into a very small area, likely heating it up and damaging the cell, and then causing it a permanent issue, even though what may have been afflicting it was temporary. So now we look at essentially the mismatch due to parallel. In this case, we'll assume that we have all cells in each one of these strings, all 7 of them, matched up perfectly. But the 2 strings themselves may or may not be, whether they're a little bit of a distance apart or the temperature is a little bit different. They're going to have a different voltage on both of these strings. So if the voltage across here is, say, 7 volts, the voltage across here is 6.9, you have a 1 volt or 0.1 volt difference. That 0.1 volts is essentially going to mean that you want to try and equalize the voltage across here. And so you're ultimately going to be pushing current back into the other one. And so if that's a large enough disparity, you'll ultimately be able to push current back through the whole entire stack. And certainly that's a bad idea. So what ends up happening is you put a little diode out here, so current can only flow out. But that diode's going to introduce loss. And so certainly you don't want to have too many diodes, because that's going to cause you additional losses and additional components. But if you don't have enough, then you're stuck with strings that may have issues. The same applies to here. You could put a diode across this. So if the voltage across here becomes reverse biased, you have a diode that just bypasses it and it's done. But usually we're not willing to put a diode across every single cell. You have 60 diodes across every cell, and each diode has to handle the current through that string. And so it becomes a relatively expensive and not necessarily a more reliable viewpoint, because the expense is high. You use very inexpensive diodes, which are prone to failure. So if we look at this, we obviously need equal voltage. And because it's not going to occur, we have to have some sort of diode for protection in there. And that's actually typically what's done. So we'll talk a bit now about the centralized and distributed architecture. So now we know a little bit about the cells. We know a little bit about some problems you get when you start stacking these things up and making larger arrays. But the more interesting part is when you build a big system, what are the options that you have? And why do you select one over the other? And there are some new system architectures that have been developed recently, at least commercially brought up recently, that address a lot of these issues. They bring up a few others, but they solve a lot of problems that we currently have. They're not new. Like most things in the power area, what's old is new again. Because when it was originally conceived, many of these ideas were just completely infeasible in terms of cost or performance or some aspect of that. And so they were shelved. It was a good academic project. They were tossed aside because it wasn't practical. But years later, decades later, they're found to actually now be something you can produce and do so effectively and inexpensively. And so there's a sort of a resurgence every time the technology slowly builds up. We can now re-access some ideas that were put up in the past that weren't possible at the time. So the centralized inverter is pretty much your standard classic inverter and system topology. So you take each one of these modules. Each module is made up of the 60 cells. And now you put each one of these modules in series. So if each module itself was maybe 60 volts, maybe 40 volts, depending upon what type of module you're using, you add up a bunch of them to get a relatively high DC voltage, and then you feed it into an inverter. Most inverters will maybe attach to three-phase systems, maybe at 480. Some only go to 208. But if you assume that it's 480, then it has to build a DC bus going into that inverter that has a value greater than the peak of the line that it sees. And so ultimately you're looking at voltages in the 300, 400, 500 volt range. So in order to get those, you have to have a large number in series. But we learned when you have a large number of these in series, you end up getting losses due to mismatch. And now that each one of these is geographically located across a larger area, the incidence of these essentially having mismatch are even higher. So what was good in terms of being able to make a module with well-matched cells, now we have to make sure we have well-matched modules as well. If you're building a couple megawatt solar farm, you can probably get the manufacturer to help you out with that. If you're a homeowner or a small commercial installer, the luck of getting that is not so great. And so it's very hard to ensure that those are going to be well-matched. And so that's a bit of a limitation. From an installer standpoint, high voltage DC can be dangerous, particularly because you can't turn it off. If you decide to disconnect the central inverter, it really doesn't matter, because if there's sunlight outside, that array has voltage. And it becomes a relatively large safety issue, and so there's a fair amount of effort that goes into protection mechanisms, insulation of wires, and all sorts of different standards that have to be followed in order to get this to essentially meet code. Now, we've been doing this for a very long time as an industry, and so everybody's pretty good at it. So it's not really that big of a deal, but you have all these complications that cost money, and it is a fair amount of work. And then the other issue, of course, you have limited flexibility. You pick an inverter that's sized for the array you have. If you're installing it on the top of your house, you fill your house with solar modules, then you're done. You buy the inverter that matches the power level and the voltages that you have, and that's it. You don't have to worry anymore. But if you can't afford to do that immediately, and the other direction to think is you don't want to, because right now you can maybe buy the top technology in cells, and what you're going to get instead is something that works okay. In 5 more years, you're going to get something that works better, and 10 more years down the road, and so on. And so it doesn't necessarily make sense to make an investment in a set of solar modules for your home that has a 20-year time horizon for payback, when you could do a third or a half of it now, and then when the new technology comes out that helps you accelerate the return on investment, then you're better off doing that. So the flexibility in here is actually an issue for residential, maybe for commercial, but really a non-issue for very large installations in industrial and utility scale. The other issue, as we mentioned with mismatch, finding that peak power point can be difficult. Because you're limited by particular cells, particular modules, the whole sum of them essentially is what you see at the inverter. And so that inverter has to take the maximum peak power point that it's looking for on the array, and it's essentially compromising because not everything is matched. That point is not going to be the ideal one for every one of these modules in the system. And so you have one place to actually control that. And so you're going to be missing out on what the potential would be for all of the separate modules. The other issue, single point of failure. This is actually a really big deal in large systems because these string inverters, while relatively reliable, they do fail, and they're horrifically expensive. And so most places are not going to have an extra one just sitting next to it on the pad for when the first one fails. So then you essentially have an array. The whole array goes down. So if you're at a megawatt size, your megawatt size array goes down. You wait to get a replacement inverter. Assuming that the manufacturer has one, they can get it there in a day or two. And if they don't, the manufacturing lead time on that may be quite some time. And so now you're stuck trying to essentially take care of that problem. A lot of that's predicated upon how much failure people believe will actually happen with these inverters. So the more recent commercial introduction of an alternative structure is for the microinverters. So I took these out of order, so we'll talk about the hybrid approach after this. But with the microinverter, you essentially duplicate the inverter on every single module. And immediately flags go up, that's expensive. You have to duplicate all of this hardware on every single one. You build a little tiny power converter for each one of these little green blocks that takes the low voltage 40 volts DC out of each module and bumps it up to whatever AC voltage you're using. A lot of times these are targeted at residential, and so they'll do the US split phase 240, 220 volt phases. And occasionally now they're moving into the 208 three-phase, and there's been some rumblings about trying to go to a 480 three-phase as well. Higher the voltages, you have a larger voltage transformation ratio you need, the more difficult it becomes. And at higher voltages, the protection of these circuits is even more important. The performance of the high voltage semiconductors aren't as good as the low ones, and so there become some trade-offs there. And so with designing each one of these power converters independently, we have the trade-offs of simply having to make a bunch of them. But now we get economy of scale. So what would have been one of those pictures before with the 200 kilowatts on top of that, that warehouse, I forgot how many modules it was, roughly on the order maybe 500-ish. Normally that might have been one inverter. Well, now it's 500. And so instead of doing low volume manufacturing, which is relatively person intensive because they're relatively complicated in terms of just their internal wiring, you have a bunch of small inverters that can essentially be manufactured using the techniques we do for consumer electronics or any high volume electronics. And so you start to shift costs a little bit lower than you would have had you assumed that they were similar in terms of labor as the larger ones. The other nice benefit here is because they all go to direct AC, if you cut the line to the grid, due to UL regulations and IEEE standards, they are required to turn off. So that means if you flip the switch on the back of the house to de-energize your array, it's off. According to the requirements that these things have to meet, it's no longer live. So you can go up on the roof, you can play with the wires, and nothing is energized. If you were to do that in a DC system, you would still have high voltage DC floating around, and that becomes a big issue. This is a very large issue in the beginning for firefighters in different areas, because if you're trying to put out the fire on a home and it's sunny out, then you're going to have live voltage there, and you can't get the voltage out from each module. And so ultimately what the initial methods were is you put large heavy blankets, dark blankets, over the top of the array to de-energize it during the day so you can actually do something with it. In a similar way, when the Prius came out, no one knew what to do with the batteries and the high voltages, and so oftentimes they just let it sit there and burn. They did not know what to do. And so that's been sort of taken care of in a number of ways for the DC side, but the AC side, it's just an inherent requirement that it has to meet. due to the fact that it's connected to AC. This also allows you to do a very, very flexible installation. You can just keep adding them as you want. 1, 2, 10, 23. Doesn't really matter. Each one of these little tiny inverters that attaches to the module is essentially designed for a particular module or module range. And so in that case, all you need to do is buy today's technology module that matches up with today's technology inverter, and you plug it in on the connectors you have on the roof. Not 100% that easy. Connectors are always a bit different, but essentially it works that way quite consistently. One of the larger benefits, and this is often difficult to get across in the power system side, is that even though, if you were to make the assumption that each one of these little tiny inverters is as failure prone or more failure prone than a centralized inverter, the system level uptime is going to be substantially better than what you would get with a centralized inverter. Centralized inverter dies, the whole thing drops out. You lose, say, 100 kilowatt for a given period of time until it's fixed. If these things fail, and even at a factor of 10 more than centralized inverters, then 1, 2, 3 of them fail. Well, now you lost 3 modules out of your 500. Okay, well, you decide next week you'll go out there and repair them. You'll replace them. No hurry. You're only losing a small fraction of your total output. And so this sort of redundancy and sort of distribution aspect inherently gives you a benefit in terms of scheduling maintenance and taking care of things as they fail. You don't have to necessarily proactively attack these things and go figure out and monitor their health. As long as you know when they died, you can just go replace them whenever it's convenient. Wait till 20 of them die and then go out and replace 20. It's very expensive to get someone in a truck to drive out and go to a place and actually do the replacements. So the cost is a big benefit on this. So the centralized inverter groups were always saying the microinverters were never going to happen for a very, very long time. Within the last year, a number of them have announced they're making microinverters. So they've recognized the benefits. But in order as not to cannibalize their existing entire business models, what they decided to do is you keep this big centralized inverter, and instead what you do is you take the best part of the distributed side that you'd normally get with the microinverters, and you put a small DC-DC converter on each one of these. So now you only have to go from some low voltage DC to some high voltage DC, and that's it. You don't have to do DC to AC with the grid interface and all the other complications. And so you can make a substantially smaller, less expensive, in theory, more efficient converter for these. And so that seems like a really great idea. But then that voltage feeds back into the centralized inverter, and its losses are then compounded. And so the total system loss here is not really any better than you would get with a centralized inverter or even the microinverter side. But what this does get you, in my opinion, is a very important aspect, is it gets you a bit of safety. Each one of these can essentially be commanded to turn off, and so they will de-energize their outputs. They can detect if there's a fault on the high voltage bus and turn off. And more importantly, they can do peak power tracking individually in every module. In the same way that the microinverters can, if your modules are mismatched or you've decided to use different types of technologies on your home because the ones you bought 20 years ago are still producing power, but they're not as good as the new ones, so you bought a couple new ones. Well, when you have these distributed architectures, you get the maximum peak power out of all of them, out of each module. Now, if each module has its own internal mismatches, there's not a lot you can do when all you have access to is the output terminals of that module. But this essentially allows you to get pretty close. And so this has allowed some of the residential installations to avoid doing microinverters. Residential installations end up with lots of shade. And so in that case, these will allow the different modules to perform close to their peak versus essentially dragging down the whole array with a centralized inverter. So they cover that. The installation flexibility here also comes in, and same with the microinverters. But we still have this single point of failure as well. So until we have a DC bus that we're using, we still have this AC inverter, and we're still stuck with that as our single point of failure. So we sort of need to justify the existence of all of this. And so there's always the question of how much does it cost? What do I get out of it? Industry doesn't really care how great the technology is unless it gets them something they don't have. And ultimately that means money. If you're making a megawatt-size installation, it's not because you're interested in generating power and making the world better as much as you are making an investment that's going to give you returns on that investment. And so they push it all the way down to the penny, down to the washers, the screws, the mounting brackets, the grounding straps that have to connect, everything that you can think of that would go in, every incidental you might run into, the number of man hours to turn certain connections. They've done it all, they've analyzed it, and so they know what the cost differences are there. It's really hard to put a number on what the cost benefits are to a technology that in some cases works really well if you have mismatch and partial shading. It may not work so well if you're in the middle of a field with absolutely no obstructions and perfectly matched arrays. So this happens to be a study that we did at the company I was at previously, where I believe this was in Vacaville, California, or somewhere thereabouts. There's really nothing there. Big fields, lots of sun, some clouds, but the weather is pretty good. And so these were coplanar arrays, side-by-side tested between a centralized inverter as well as some of the microinverters that we had made. And these are a generation or two behind. And so you'd assume that the newer ones would be more efficient and more capable. And perhaps the centralized inverters might be as well. We were able to capture a significant amount of energy more over the course of a year than a centralized inverter was. I believe it averaged out to something on the order of 10 or 15%. And so that's real numbers. That's real money that you can use to compare the two. And that's ultimately what matters in terms of adopting a new technology is, what do I really get for all of this? And so this is at least a quantitative result on the qualitative benefits that we normally get. Let's see what's left. So I ended up, when we're a little short, we have some very sparse slides. I was not able to include a number of plots and images from some of the ongoing work for various reasons from colleagues who are withholding it from public view at this point, but I can talk about it. So the next step that we're going is the microinverters at this point. They essentially look like the ones on the bottom. They're bolted onto the frame. They've got the connectors to this junction box where the wires are actually located inside. This is another similar version of it as well. This is an N-phase system that's OEM'd by, I believe, Westinghouse for their large-scale installations. But what this is sort of doing is you can sort of see, you want to mount this directly to the module. The way it's been done for a long time is you mount it to the rack, you then connect it up, and that's it. You don't have to worry about making sure that you buy a module that it has a particular inverter on it. No modular manufacturer necessarily wants to commit to a particular inverter manufacturer. Each of them have different lifetime warranties. Each of them have more interest in their own product and then who's the one who actually supports it, who does the warranty. And so what's been going on for a long time is they'll buy the inverters and they'll bolt them to the frame as a third party, and then the third party actually uses that in the installations. The direction this is moving, and has for a while, is essentially to remove this junction box where all of the little connectors of all of the strings essentially collect, and mount the box right there. Not only do you get rid of the junction box, these cables that go in, you essentially have a nice modular system that if it fails, you can pull it out and put it back on. Or if the module fails, you can take the module off and put a new one on for that inverter. And so it still becomes modular. The industry is still moving on what is a universal mounting plate. This is a point of contention, like most things. DC connectors for electric vehicles has been a contentious debate for a long time. This one will be on for a while as well. So as you place these here, if you just mount it on there and you treat it like a standard module, that's fine. You've at least gained some benefits by not having junction boxes and wires. But by removing the junction box, you now have access to internal wiring on the module. So the module is normally 60 cells in series. But what it really is, it's 3 strings of 20 connected in series. And so in the back of these, you essentially have 30 cells, and then the wires attached to it, 30 more cells and the wires attached, and 30 more, or 20 more and the wires attached. And so you have access to all of those. So now, if you want to improve upon possible mismatches, you can deal with 20 cells at a time in series instead of 60. And so there's another benefit to going even deeper down into the module to prevent a bit more of the mismatch issue. Part of it being that you can now probably make modules that don't have the same cells from the same bins. You can make modules with 3 separate strings from 3 separate bins and not have to worry about the matching. To get a high-power module, to get the top cells all from the same bin is much more expensive than getting the less expensive ones. And so if they can mix and match to control their own inventory and power output, that's something they're definitely going to be very happy with. So, didn't pop out at the top. The cell level conversion and substring. So it's going to draw up on here. The strings normally operate from a connection to the top, down one side, around the bottom, and back up. And the next one is the next string, and so you have the 3 there. So if you go ahead and you say, okay, well, if we're going to decide to actually go and do substring, we had big arrays, now we go down to individual modules. If we really integrate with the module, now we can get substring. Well, why don't we just go all the way down to cell level, and how much further can you really go? Cell level is hard. Cell level is very hard in terms of the fact that, as we talked about with the cells, you get half a volt, maybe a volt, and 5, 10 amps to deal with. The level of conversion that you need in order to process this is really large. You have massive amounts of current, but very little power coming out, and so most of the losses are going to be resistive, and there's just not much you can do about that. So one of the techniques that is moving forward, and I can happily talk to people about this afterwards, is what they're calling partial power processing. So what you do is you still keep all your series connected cells, but each cell still gets its own little tiny power converter attached to it. So if you assume that you have a mismatch in a series of cells, and you're going to be limited by what you have, by the worst one, why not have a little tiny power converter for each cell that only siphons off the extra amount of energy that isn't being taken already by the series connection of the string? So if a whole bunch of, you have 10 of them that each can put out 10 amps, one of them is limiting it to 5, well, now you have 9 others that could still be putting out 5 more amps. And so these little converters will essentially take and convert those 5 amps out, connect that string in series as well, and then add it to what you already have. And so essentially it's a way, instead of having to process the full amount of power and the same amount of current that you would normally have, you can process through power conversion only a small amount and still get the same benefits as if you had cell level full conversion. And it would be substantially less expensive and substantially more efficient. And so this is something that's actually under development, and there are a few different ways that these are working. People are working on it, but unfortunately a lot of it is not necessarily public or not desired to be at this point. And so there's only so much you can really do about it. So that was sort of picked up when you go down to the cell level. Well, partial power processing also scales back up. So if you look at the module level again, instead, when you have series connected modules, you can do partial power processing on each module that's connected in a series string to avoid any mismatch in those strings as well. And so the majority of what's being developed is essentially scalable. You may start with one cell, but then ultimately you're making one larger cell in a module. And then when you make a big string of those, it's an even larger cell. And so the same issues come in at all of the different levels that you end up with. And it's really a matter of at what point do you want to actually jump in and start breaking it down. The analysis on where that point occurs is challenging because it primarily depends upon what technology is available at the time. Up until recently, it really wasn't beneficial in order to do it at the module level. Now, with the cost of electronics coming down, manufacturing volumes going up, now it looks very attractive. And so that's the direction things are going. If we can make efficient enough power converters that land for each individual cell, then it's likely that it'll go that far. But from a benchmark standpoint, one really large DC-AC inverter, very efficient, very expensive, it's probably in the 98% range. It's pretty good. The best, at this point, microinverter that you can get, at least on the market, publicly announced, is at 96.1. So certainly that's less. But the energy capture that it can get is larger, and so ultimately it still ends up having a higher captured energy. As you go down to substring levels, you end up with other issues. The DC optimizers, the DC-DC converter, maybe it's 99% efficient. Okay, now you connect it to a 98% efficient centralized inverter, and now those cascade, and now you're back down to what you would have if you just had microinverters. And so that's one of the biggest trade-offs, is where is the efficiency going, and how much power are you going to lose by gaining some extra power due to the architecture that you've designed. And so those are most of the issues that are difficult to balance. And so reading the tea leaves and predicting the future on where it's going is quite difficult. But at this point, it's definitely trending towards the cell level. And there's really no question about that. With advances in the power converters based on ICs, it is moving to the point where people are hoping to actually fab the power converter right on silicon, which is used to make the solar cell. In which case, the solar cell has its own built-in power converter, and its output is perfectly optimized for its peak power. That's sort of the holy grail that everyone would love, especially if it was free because you were doing it on the same process as the cell itself. At this point, they use different processes, and they're not terribly compatible, but all of this is going in that direction. So primarily, that is all that I have. And so I'm hoping for some fair amount of questions. And so I will hold off and hope for some questions here.
Thank you very much. Any questions for Brandon?
Yeah.
With the existing technology, if you have strings that are slightly mismatched in voltage, and you protect them by series diodes, now what happens to the low-performing strings? Are they just not participating at all because their diodes are back-biased, or do you pull the bus voltage down under load until they're all contributing something?
It depends exactly how far off they are. If they're only off by a few percent in terms of their mismatch, what ultimately happens is if you just let them open circuit, their voltages would be a little bit different. And so ultimately, their peak power is a bit different. So the open circuit voltage compared to the voltage at which the peak power occurs is usually about 70, 80% from the open circuit. And so you end up bringing those voltages down anyway. And so you're always going to be operating, unless one is really far down because there's something majorly wrong with it, you're going to be operating both and pulling current out of both. Except the difficulty is finding what is the right maximum power point to track. You'll end up tracking the one that has the best performing string of cells. But what that means is you're no longer at the peak power voltage for that other sub-performing string. And so you can't actually get out the peak power of that one string that's behaving oddly. You're pretty much you're pulling the highest out of the one string and less than optimal off the other one. And the same thing goes for voltage versus current as well when you do the trade-offs. And so each one is self-limiting. When that diode becomes reverse bias is essentially when its output voltage does not match or does not even get to the point where the peak power voltage is that the whole array is operating at.
Other questions?
Yeah.
Compared the peak efficiencies of the centralized and the microinverter and hybrid system, how do those efficiencies fall off when the three systems compare to each other when you're not operating at the optimal point?
Good question. You mean so how do the efficiencies vary over non-optimal points?
The whole operating range.
Yeah, so if I'm guessing, that means that if instead of being at full power, they have one efficiency when they're operating full power, and then partial sun, they're operating at a different power level. And how does that efficiency vary? So most of these efficiencies are not necessarily peak efficiencies. So the California Energy Commission, CEC, has a very, very nice set of standards that everybody copies. California always was ahead in the solar range. They picked up the standards. They wrote most of them with Sandia National Labs, Lawrence Berkeley. And they came up with a way to try to average out so you could just pick one number. And so they say you measure at 100%, 75, 50, and 20% average power, And then there's a weight that goes on each one of those. I think it's a single-digit percent at 100. They assume you're never at 100. The 75 and 50 are the most heavily weighted, and then the 20, and then maybe it goes all the way, or 50 and then down to 20, then trails off. And so their assumption is you're primarily, if you design the system well, primarily running in the 40 to 80% rated power range. And so that's where they actually focus their the weighting of the calculated efficiency. And so that's ultimately how they come up with a number. So even if an inverter had a peak efficiency of 99.9%, its CEC weighted efficiency may be much lower. Because otherwise you could really game the system quite well. And they still can, even with the testing procedures, but it's much more difficult to do so. Yes?
What is the influence of power electronic devices which are inside the AC-DC inverter to the existing AC network? Since if they contain power electronic devices, they probably deteriorate THD, total harmonic distortion, introducing the higher harmonics, third and fifth order. So if every house in Seattle would have inverter, how would that influence the network?
Okay, so the question is, because it's all power electronics inside these converters, they have noise, they may emit harmonics onto the grid, and therefore cause all kinds of problems, or potential problems when you essentially get a really high rate of penetration. So part of that's addressed by the fact that there are standards for this. There are standards for exactly what the THD you can put out onto the grid is. It's pretty good constraints. I mean, you're talking about semi-residential devices. And so there's a level that they have to meet. And everybody meets it. And so in theory, it all averages out. Now, if for some reason all of the inverters got synchronized at their switching frequencies and matched up perfectly, you might, as an aggregate system, be able to generate higher THD than would be allowed. But for each individual inverter, that's the unit that's actually tested for the harmonic content. There are a lot of concerns with what happens during transients and what is the best way to handle strange behaviors when the sun decides to magically disappear and then immediately reappear. And so there can be issues with that when all of a sudden, if you have a very large amount of power around an area, you lose 20 megawatts worth of power in a matter of less than a second. And then it shows up again 2 seconds later. There are a lot of issues involved in that, as well as even what happens when the grid disconnects and now you're at an island. Right now, most of the procedures are, if it goes outside of a very strict bound, shut off. And it sounds great because everyone knows the behavior. Problem being, of course, that if you have a high penetration and some voltage range goes slightly out of spec, they all just shut off. And it may be a completely arbitrary reason that voltage just had a little spike on it, or the frequency drifted out for just a second. And so there are new regulations coming in and being adopted, a lot of them based on what came in from Europe, on how to handle riding through low voltages and different frequency ranges and things like this, including reactive power transfer. And so it's a relatively active area of investigation, both in research and even in industry, so everyone gets along.
Is it feasible to use batteries in order to
Yes.
get rid of this voltage drops and stuff like that?
Yes, so the question being, is it possible to use batteries to sort of take care of that? And the answer is absolutely. And so this is something that you could look in the future and say that a lot of things are going to move towards DC. And so having energy storage in a home or your electric vehicle plugged into your home would help to then be used as energy storage to smooth the transients, at least to a particular rate of change. So you may not drop out anymore, but you limit it to a certain slew rate. That is absolutely something that is doable, and I'm actually imagining that will become a requirement to a certain level. The transient response will likely allow somewhat sharp changes, but at this point, most inverters have only the minimum necessary energy to handle the AC line energy storage, and so they get maybe 1-2 cycles worth of energy, and they're done, and they've depleted it. So if they could ride out for 20 or 100 cycles, that would make a massive improvement in stability.
Okay, well, let's thank again Dr. Brandon Pierquet for this very interesting presentation.